Hello everyone. We are Team 34 and our project is focused on adapting object-centric dexterous manipulation policies for unseen dual manipulator robots. The core challenge here is bimanual dexterity. Real-world manipulation requires precise coordination between high-level planning and low-level finger control. Current systems lack the fine-grained motor control found in humans. Our goal is to bridge this gap to create scalable systems for tasks like industrial assembly. Our specific task involves re-implementing and improving the Arctic and Objects-Ends baseline. Arctic is the dataset we use that provides us with high-res bimanual human manipulation sequences, including video and motion capture. However, unlike previous approaches that relied on this privileged motion capture data, our input is strictly RGB images. From just these images, our model must output both high-level wrist actions and low-level finger joint angles in a simulated Isaac Gym environment. Here is our approach. The prior baseline used a hierarchical policy that depended on human mocap data. As you can see in the diagram, they utilized a higher level wrist planner that takes motion capture data and feeds to the model. We replaced this dependency by just using RGB sequences as input. This predicts object and wrist trajectories, which then guides a low-level finger controller to execute the grasp. This allows us to operate without explicit mocap during inference. Their architecture uses a CNN on the mocap data to get feature embeddings, which is then passed through an MLP regressor to get the mano poses for both hands and the object's poses as well. We replaced the MLP regressor with a transformer-based decoder. We designed a specific transformer-based decoder pipeline. It takes the visual feature map and processes it through a transformer decoder. The output is then split into specialized linear heads, which are responsible for simultaneously reconstructing the left-hand manomesh, the right-hand manomesh, and the object model.
The training curve shows stable descent, with the loss reaching 0.01 before overfitting starts at 10K steps. We trained using a cosine annealing learning rate schedule with Adam W, batch size 256, and a transformer decoder with depth 12 and hidden size 512. For object mesh reconstruction, both the 3D key point loss and the rotational loss show a stable smooth descent, dropping below 0.02 before overfitting kicks in near the end. Since the hand and object meshes are produced jointly by the same transformer with only different mano-style heads, the training behavior mirrors the previous slide. This consistently shows that the model learns both object geometry and orientation reliably. Let's look back at our baseline, the ArcticNet SF architecture. There are two major issues here that the transformer solved. First, the scale of the loss. Here, the loss oscillates between 16 and 22. In our new transformer model, we were down to 0.01. Secondly, the shape of the curve. It is jagged and unstable. Here, it struggled to balance the combined losses of both hands and objects, whereas the transformer separated them and minimized them smoothly. This really shows why transformer-based approach was the right move. Finally, the generated data was then sent to our low-level PPO controller. Here, the agent successfully learned the trajectory execution, climbing to a maximum reward of 350. This shows that the trajectories generated by our transformer were correct, and the rewards learned by our PPO were also correct. Further, moving on to our results, here the ground truth is shown on the left and the predicted mesh on the right. Both don't overlay on the object directly due to missing camera parameters. However, they are accurate trajectories in the world frame. This is validated by a low-level controller execution, which is shown in the next slide. Here, the two arms, which are trained using our PPO policy, approach the object and manipulate it in the desired trajectory. The PPO model uses the trajectories generated by a transformer decoder. The metrics we're tracking are mean per joint position error, which is the L2 distance between the 21 predicted and ground truth joints for each hand after subtracting its root. Success rate is the percentage of object points we reconstruct accurately. Over various objects, transformer-based decoders significantly outperformed the ArcticNet SF in JPE and success rate. The numbers here are relatively low due to the overlay error caused by missing camera parameters. In addition to missing camera parameters, we also faced issues such as missing files and documentation from our baseline repository. Additionally, compute limitations made it significantly difficult to process 2.1 million high-res images. By successfully substituting the mocap with our RGB-only inputs, we validated a pipeline that requires only standard cameras, removing a critical hardware barrier. Moving forward, this pipeline will be tested on different arms to test cross embodiments, and the model will be defined to account for missing information, such as camera parameters. Additionally, we will perform experiments with different objects and motions. Here are some of the references which involved the objects, Arctic, embodied hands, expressive body capture, and end-to-end recovery of human shape and pose.